Hi everyone. So we are continuing with the current electricity, and today we will see this example number 20. So here you see in this question you can see a galvanometer together with an unknown resistance in series is connected across two identical batteries of each 1.5 volt. When the batteries are connected in series, the galvanometer records a current of 1 ampere, and when the batteries are in parallel, the current is 0.6 ampere. What is the internal resistance of the battery? That we have to calculate. Now here, so 1.5 volt, you can see these two EMFs. So a and this is the galvanometer. Okay. Now galvanometer together with an unknown resistance in series is connected. So there is some unknown resistance which is connected in series with this. It's connected across two identical batteries of each 1 point. So EMF of this cell or this cell, it is 1.5 volt. When the batteries are connected in series, the galvanometer records a current of 1 ampere, and when the batteries are connected in parallel, the current is 0.6 ampere. So now let us consider. So let R be the combined resistance of the galvanometer and the unknown resistance. So let small r be the internal resistance of each battery. Small r, internal resistance of each battery. So the total resistance of the circuit, it will be how much? Combined resistance of the galvanometer and the unknown resistance. Capital R is because there may be some resistance of the galvanometer and there is some unknown resistance which is connected in series. So it means the equivalent, it will be, let us say R dash plus R, where R dash is the galvanometer resistance. So that equivalent, it is taken as capital R. Now there are two internal resistance, one for this and another for that, that is small r, as well as this is small r. So that equivalent, it becomes R plus 2R. The current, it will be how much? Because both the cells are connected in such a manner that both are having the tendency to release current in the same direction. So effective EMF, it will be E plus E, that is twice of E. So twice of E upon total resistance, so it is R plus 2R. So we are getting this current. So current, it is given as 1 ampere. This is 2E, it is also given, that is 3, because 1.5 volt each, so twice of it will be 3 divided by R plus 2R. So we are getting R plus 2R, it is equal to 3. Now in the second case, since the batteries are in parallel, the EMF remains unchanged. So the effective internal resistance becomes how much? R by 2, because now the cells are connected in parallel. So here internal resistance R, here internal resistance R. So equivalent of these two, if they are connected in parallel, it will be 1 upon R plus 1 upon R, reciprocal of that, and finally it will be R by 2. So the current, it will be how much? E. E upon this R plus R by 2. So that it is twice of E divided by 2R plus R. Now you can see this here. Why we have taken this E? Because these two are connected in parallel. Now they are connected in parallel, and if you consider this galvanometer, so EMF across this point or this point, that remains same as E. This clear? Because in series, equivalent between these two, it becomes twice of E, but equivalent between these two, it is E. Here also it is E, here it is also E. So that's why we have considered this E. So E divided by R plus R by 2, and finally taking LCM, simplifying, we are getting this. Current in this case is also given. So we have again R, 2R plus R. We will have a relation here. That is 3 divided by 0.6. Now we will have two equations and two unknown. Here you can see the second connection, 1.5, 1.5, and this is G. So now we have two equations and two unknown. Simplifying, we can calculate this. So just simplifying both that, we are getting internal resistance, this R, it is equal to 1 by 3 ohm, and that was to be calculated. Now in this question you can see there are 12 cells each having the same EMF are connected in series and are kept in a closed box. 12 cells each having the same EMF are connected in series and are kept in a closed box. So here suppose we have all these cells, 12 cells connected in series and having the same EMF, and they are just put in a closed box. some of the cells are wrongly connected. The intention is to connect them in series. So when you connect them in series, so plus minus, it should be connected like this. But some of the cells, if it is connected, suppose like this, it means these two cells are connected opposite to this. So it means this is violating the series connection which is required, or which is assumption, or which is the intention. So the cells are wrongly connected. This battery is connected in series with an ammeter and two cells identical with the others. The current is 3 ampere. When the cells, the current, because ammeter will record the value of the current, so it is 3 ampere when the cells and battery support each other, and is 2 ampere when the cells and battery oppose each other. So when they are supporting each other, the current here it is 3 ampere. When they are opposing this, 2 ampere. So how many cells in the battery are wrongly connected? So that we have to calculate. So again you can see, let X cells be connected correctly and Y cells be connected wrongly. So the total number of cells, there are 12. So it means X plus Y is equal to 12. Now the net EMF, X cells are connected correctly. So it means the total EMF will be how much? X into E. X into E. Y are corrected wrongly, it means Y opposite direction of this X. So it will be Y into E. So net EMF it will be how much? X y, E minus Y, that becomes X minus Y into E, where E is the EMF of each cell. Now let R be the total resistance of the circuit, which remains always constant, because whether you are connecting the cells like this, higher and lower this side, or whether you connect it like this, the resistance here, if it is R, here it is R. So finally they will remain same. The EMF, it will affect the effective EMF, but the internal resistance or the resistance of the circuit, that will remain same. So now when the battery and the cells support one another, when the battery and the cells support one another, the net EMF it will be how much? Of the cells it is X minus YE, and battery, there are two batteries, so it becomes plus 2E, because they are also support. So support, this is supporting this, so it will be added. Now when they oppose, so this and minus this, yani this will be opposite to this, so they will be opposing that. So effective EMF here it will be X minus YE minus 2E, here it is X minus YE plus twice of E. Now the current I, it will be again how much? Net EMF upon total resistance. So in the first case, the current it is 3 ampere, that is given. So X minus YE plus 2E divided by R, this one. And in the second case, you will get X minus Y into E minus 2E upon R. Now again simplifying these two equations, we will get whatever is desired. So if you divide them, so this R and R, it will be eliminated. We will get this equation. And again you can multiply, cross multiply, and then you can simplify that equation. So here if you see, if you can see, after cross multiplication you are getting this X minus Y is equal to 10, and X plus Y is 12, because this is the total number of cells. Simplifying these two equations, you will be able to get values of X as well as Y. So X is 11, Y is 1, means X cells or 11 cells are connected correctly and one cell is connected wrongly. That means in the opposite direction of all these 11 cells. So this will, so only one cell is wrongly connected. I hope this is clear. Now here in this example you can see two cells of EMF 1.9 volt and 1.1 volt and internal resistance 0.1 ohm and 0.8 ohm respectively were connected in parallel in a circuit. The cells were loaded by an external resistance of 10 ohm. Find the magnitude and direction of the currents in each cell and the work done in 1 minute in the external circuit. So again you can see the question. Two cells each of EMF 1.9 volt. So sorry, 1.9 volt and 1 point. They are having two different EMFs. 1.9 volt and 1.1 volt. And internal resistance is 0.1 ohm and 0.8 ohm respectively. We are connected in parallel. So these two are connected in parallel. the cells were loaded by an external resistance of 10 ohm. Cells are loaded, this means when we use all these statements, this means they are connected across an external resistance of 10 ohm. So external resistance of suppose 10 ohm here. Find the magnitude and direction of the currents. This cell is loaded with this. So it means here again another cell is also loaded with this. So again here. So these two are connected in parallel, and finally the circuit is loaded with an external resistance of 10 ohm. So we have to calculate the current and its direction in each cell. So here, if you consider current coming from this cell, it is I1, let us say I1. Current released by this cell, it is I2. Individually, they have the tendency to release from higher to lower, but we can assume any direction. So here, let us say it is I1 and I2. So finally, at this point, from this it is I1, from this side it is I2. So this will be I1 plus I2, and let us say it is equal to I. So through this external resistance, the current flowing is I. Now, so I1 plus I2 is equal to I. Now, in the loop A, B, E, F, A, and in this loop. Okay, now if you use the Kirchhoff's rule, so you will find A, B, E, F, A, 1.9, this is 1.9. So first let us say summation of IR is equal to summation of EMF. We will use this relation as far as the Kirchhoff's rule is concerned. Potential difference, sum of all potential difference across all resistance, it is equal to sum of all EMFs. So I1 R1, so 0.1 into I1. 0.1 into I1, this is internal resistance of this, so 0.1 into I1. So we are proceeding in this direction. Okay, so this current I1 is having the same direction as we are moving along this loop. So that will be taken with the positive sign. So 0.1 into I1. But we are moving from B to E as far as the circuit is concerned. But this current I2 is having direction from E to B. It means it is in the opposite direction of our movement. So if you take loop movement as positive, then the current particularly in that segment or particularly in that region, it will be taken with the same sign if it is also moving along the loop of the circuit, that is assumed. Or if it is in the opposite direction, then it will be taken with the minus sign. So here we are moving from B to E, but the current is having tendency to move from E to B. So it means it is minus sign. So minus of 0.8 I2. It should be equal to how much? Sum of all EMFs in this circuit. Now see how the EMFs will be considered. Now again this cell, because exact direction of the flow of current right now we don't know, but we have assumed here, and we know that the tendency to release current, it is always from the higher to lower. So this cell is having tendency to release current from this side. From this side means in this direction, and we are also moving in this loop from A to B, B to E, E to F, and F to A in this. So tendency of this and movement here both are in the same direction, so it will be taken with the positive sign. So plus 1.9, so plus 1.9. But this cell is having tendency to release current this side, but we are moving from B to E, that is in the opposite direction. So minus of 1.1. So 1.9 minus 1.1. This is clear. So now simplifying this, summation of this EMF is equal to summation of IR, or vice versa, summation of IR is equal to summation of EMF. Similarly, consider the second loop. Second loop means ACDFA. I will just remove all this. Second loop is ACDFA. Yani the bigger one. So in this bigger one, you can say again I1 into 0.1 this side. Okay, here it is how much? Total I into this R, or this 10 ohm it is given. So you can consider again 0.1 into I1 plus 10 into I, because here it is I and this is 10. So 10 into I, that should be again how much? The net EMF in that circuit. So net EMF means in this circuit. So here again it is 1.9 with the positive sign. There are no other cells connected here, so it will remain same as 1.9. So it is 1.9. So 1.9 is equal to 0.1 I1 plus 10 I. Now again, just simplifying these two equations, you will be able to get point I1 as well as I2, because there are only two unknowns and two equations. Simplifying, we can calculate I1 as well as I2. So the total current flowing through this resistance, the external resistance, it will be I1 plus I2. So that gives us this I. Now work done. Work done, it is how much? I square R into time t. So I square R into t. So I, it is known to us. R is also time that is given. In 1 minute we have to calculate. Simplify and we are getting this much of joule. So this is the work done. That is also the heat which will be generated, and that is nothing but the work done, which gets converted into heat generation. And from here we calculated I1, I2 as well as I. So now see this equation, this question. So here in this question, two resistors A and B are in parallel with each other. A and B are in parallel with each other, this as well as this, and in series with a 200 ohm resistance. So here you have this series. You can see, if you see this circuit, okay, so these two are connected in parallel, and finally it is connected in series with this 200 ohm resistor and a dry cell of EMF 1.5 volt. So dry cell of EMF 1.5 volt. The resistance of A is 100 ohm. The resistance of A, it is 100 ohm. Two resistors A and B, the values of A and B it is given, this is 100 ohm. When B is disconnected from A, when B is disconnected and removed, an additional resistance of 50 ohm must be inserted in series in the circuit in order to keep the current through A unchanged. Means when this is removed, now when suppose this was there, then some amount of current was flowing through this A. Now when this is removed, so 50 ohm has to be put in series so that the magnitude of the current flowing through A does not change. That is the main part of the question. Must be inserted in series in the circuit in order to keep the current through A unchanged. Find the resistance of B. So that this we have to calculate. So suppose, so the net current flowing through A, it will be how much? Can we say it is E upon 200 plus this? Why 200 plus this? Because if its resistance is suppose R, then these two are in parallel. So these two are in parallel, so equivalent it will be how much? 100 into R divided by 100 plus R. So 100 into R plus divided by 100 plus R. This entire it is connected in series with 2 ohms. So equivalent it will be how much? 200 R plus this equivalent. So the current I, it will be E divided by this. Now in the second case, if the current passing is suppose I2, so that will be how much? IR upon 100 plus this R. IR divided by 100 plus R. That's why this I2 it will become how much? E. This is I here, and I2 that will be, this is your I2, any current through this, because this is the total current I which will be released from this cell. So once this total current I, so up to here it will be I. Now this will be again distributed. So some current, suppose I1 here and I2 here. Now we have to calculate this I2. Again to calculate I2, directly you can use these equations, or again let us go back to the basic. So these two are connected in parallel. So again can you say I1 into R, it will be equal to I2 into 100, because potential difference across this, and this it will be same because they are connected in parallel. So I1 into this R is equal to I2 into R. So from here you got this relation, and another relation is what? I1 plus I2 is equal to I, that we have calculated. So just simplify these two equations, you will be able to calculate I2, and if needed we can calculate I1 also. So that's why from these equations you can say we have this current I2. Now this I2 is known, which is passing. Now this resistance of this cell B, it is this resistance B, it is removed. When it is removed, just to compensate so that I2 remains same through this A, we need to put 50 ohm this resistance. So if we put this 50 ohm resistance in series, now see this one. So 1.5 volt, that remains same here. Now this is removed, and 50 ohm resistance, suppose it is connected here. Okay, because 200 ohm, this and this, they are having the same nature of connection. This is no more there. Close the key, it will start working. Open the key, so it can be disconnected. So it can be disconnected with the help of key, or it can be connected with the help of this key. So in that case, the current I3, now in this situation, let us say the current I3 is passing through this 100 ohm. So again, after simplifying this, and that we can easily simplify, again we know the equivalent resistance, this and this, E upon that equivalent resistance, E upon that, because all these resistances are connected in series, so equivalent it will be 200 plus 50 plus this 100, that is given. Because don't get confused, this is here, so how it can be connected in series with this. Now this is no more, this part, because once this B is disconnected, so there is no meaning of this part. So if there is no meaning of this part, so there is no distribution this side from this side or from this side. So it means it becomes insignificant. So you have a single circuit starting from here and coming back to this point. So there is no branching this side because there are no resistances here. So here if you start from this point, so 200 plus 100 plus this 50, so all are connected in series. So we have this equivalent, which is coming as E upon 350. But question says I2 and I3 remain same, because initially whatever was the current, finally that is going through this 100 ohm resistance. So it means I2 is equal to I3. Equating this, we are getting this 400, R is equal to 400. So from that we got the value of the resistance of this B. So this way we can simplify that.